of years, in my previous lecture, I had discussed the anomalies of open chain structure, and we saw that how a cyclic structure will remove the anomalies of the open chain structure. That we shall be discussing in our future lectures. But before I do that, we've also discussed that the cyclic structure results due to reaction between the hydroxyl group on the fifth carbon and the aldehyde group, resulting in formation of two cyclic forms, that is the alpha D glucose and beta D glucose. And in order that we can explain all the reactions of glucose, we can say that all the three forms will occur in equilibrium in aqueous form. Therefore, they will show the properties of the open chain structure of glucose and also represent and also explain the properties which an open chain structure of glucose could not explain. But before taking up as to how the cyclic structure will explain the anomalies of the open chain structure, I would like to explain, or I would like to discuss the cyclic structures of glucose with you. And we know that cyclic structures of glucose can be represented by Fischer's projections. It can be represented by Haworth Parenos rings, and it can also be represented in form of chair conformation. So if we look into the Fischer projection, then we know that Fischer projections are not the best way to show the structure of a cyclic sugar, because the COC bond is representing without consideration of the bond lengths between carbon and oxygen. So as you can see on your screens, here we've shown that bond is being formed between the oxygen at the fifth carbon and the carbon, and this proton goes on to the oxygen and this carbon is converted into a asymmetric carbon, resulting into the formation of the cyclic form. And this cyclic form is the representation in Fischer's projection. So what you find here is that when we are making the bond between the first carbon and the oxygen and the fifth carbon and the oxygen, here you can see that no bond length has been considered. That is, we have not specified what is the bond length between this carbon and oxygen and what is the bond length between this carbon and oxygen, which you can see again very clearly in this structure, that the oxygen, the bond length, bond distance between this carbon and this oxygen and carbon has been shown randomly. It has just been shown that this ether linkage is formed between these two carbons. So that means the Fischer's projection is not a correct representation for the formation of the cyclic structure. That is, we cannot represent it very accurately. So what is the other projection, or what is the other structure by which we can explain the cyclic structure of glucose? So this can be done by Haworth projection. And the Haworth projection is the most common way to describe 3D structure of glucose, or for that matter any other carbohydrate. So when I'm saying any other carbohydrate, that means we mean monosaccharides. They can be aldoses or they can be ketoses, and then we can represent their cyclic structures, and we know that these aldoses or ketoses will form a glycosidic linkage when we'll get a disaccharide, and from there, if there are many means 2 to 3, 6 to 8, then we will get units then of these monosaccharides, we'll get oligosaccharides, and when there are hundreds of units of these monosaccharides, we will get polysaccharides. So that means we have to now pay attention to the monosaccharides as to what will there be, what their structure will be. So if we look into a aldohexose, and for that we are taking an example of glucose, so we can say this, the Haworth projection is the most common way to describe the 3D structure of glucose or any other aldohexose. And we know that Haworth pyranose rings represent glucose or any other carbohydrate that is as a planar molecule. So when we are looking into the Haworth projection, what we find that in Haworth projection of a D pyranose, the ring which is formed by the sugar molecule after internal hemiacetal formation, as shown in a manner as if we are looking at it from the side. That is, we are not looking at it from the front, that is down at the ring from the above. So what it seems like that we are looking at the ring from the side, and we call it as a pyranose rings because the basic structure in the ring is that of pyrane, which is a oxygen containing heterocyclic compound. So, and the next thing that we see that the sides which are nearer to us, they are shown by thick lines. So, and the groups attached to each carbon atom are then shown as they are above or below the plane of the ring. So, let us look into these examples, the two examples. This is your alpha enomer and this is the beta enomer. So, what we find here is that these lines which are in the front, they are thickened, that is they seem as though they are towards the observer here also in both the cases, and that means they are coming out of the paper, and groups which are coming out of the paper. So the bonds which are in the front are represented by the thickened lines. These are the Haworth projections, and this structure is cyclic structure. And what we find that the groups which are now attached to each carbon, they are attached above the plane or they are attached below the plane of the ring, because this is a planar structure in which the groups are in one plane, and we say it is a pyranose structure because what you find here is that the basic structure of the ring is that of pyrane, that is a heterocyclic compound which has an oxygen as a heteroatom. Now when we look at the relative positions of the primary hydroxyl groups and the OH group here, nothing is written at the below whether it is the alpha form or the beta form. Since these two groups are trans to each other, you will say this is the alpha form, and since the primary alcoholic group and OH are on the same side at the anomeric carbon, this is the beta form. All this I have discussed in my previous lecture as to what is the anomeric carbon. So now the question is, how can we convert a Fischer projection to a Haworth structure in a simple way? There are some tricks in which you do not have to go into the mechanism of the reaction in detail, because when you look into the mechanism of the reaction in detail, which I had discussed in one of my lectures on structural aspects of carbohydrates, what we found that we had to put the glucose molecule at 90 degrees and then change the position of the groups at the fifth carbon so that the OH is facing the carbonyl group, and then we went on to mechanism and the structure of the glucose molecule, that is the formation of the pyranose ring. But now we do not have to do this in a simple manner, because if they ask you draw the structure of a pyranose ring, you are not going to go into the mechanism, you just have to draw the ring. So what you have to do is, you will draw, first of all you draw the pyranose ring with the oxygen on the top right. After this, what you have to remember that the groups which are on the right hand side in Fischer's projection will go down in Haworth projections. That is, they will go below the plane of the ring, and the groups which are on the left in a Fischer projection will go up in a Haworth projection. And then the next thing that you have to remember, if the molecule in the Fischer projection is having D configuration, that is the OH is on the right hand side at the fifth carbon, then in that case the primary hydroxyl group will be written at the top attached to the fifth carbon. And then how will we differentiate between the alpha anomer and the beta anomer? In the alpha anomer, the OH will go down for D sugars, and in the beta anomer, OH will be facing up, right? So now if you look into the screen, that slide which has been coming on your screen, this is the Fisher projection. In Fisher projection, we find that these groups are on the right, that is the second chiral carbon, third chiral carbon and the fourth chiral carbon, which we have to place on the pyranose ring. This OH is involved in ring formation, that is this is acting as a nucleophile, it is reacting with the aldehyde group, and we are generating a new chiral carbon, which is this chiral carbon. And then we have this oxygen is making a bond with this carbon, that means this is this oxygen. So now if that is the case, that means this carbon will now become the first carbon. So this is the first carbon in the cyclic structure. So what you have to remember is that when you're making the structure, first you will make the pyranose ring with the oxygen at the left top, and then this carbon will become the first carbon, which has become asymmetric due to reaction between this OH and this aldehyde group. So this is that OH, that means this is this OH. Then we have this OH. So what we find that hydroxyl groups on the second and the fourth carbon are on the right hand side. So if they are on the right hand side, that means they will go below the plane. And here also what you find, that is now this is, since the OH here is also on the right hand side, that means this will be the alpha anomer that we are making. So in alpha anomer, what you have to remember, that OH on the first carbon is going to be below the plane of the ring. That means the primary hydroxyl group and OH are trans to each other. So if one is above the plane of the ring, that is at the topmost position, and this is indicating that the molecule has configuration capital D, and this is indicating the orientation of these two groups is indicating that this is an alpha anomer, because in alpha anomer the primary hydroxyl group and OH group are opposite to each other. Next what we have to now look into the structure of what will be the orientation of these groups. So what you have to remember, that the groups which are on the right hand side will go below the plane of the ring. That means the OH on the second carbon and OH on the fourth carbon will be below the ring. So we have OH here, which is at the second carbon, which we've indicated by showing that it is below the ring, and again OH at the fourth carbon is below the ring. Whereas when we look into the third carbon, what we find that the OH here is on the left hand side. So since it is on the left hand side, it will be above the plane. So this is what we have here. So this is the structure of alpha D glucopyranose. Now in case if you have to make the structure for beta D glucopyranose, what you have to remember, now you know this is alpha. So what is the difference between alpha and the beta? In beta only the orientation of OH at the first carbon is different. At rest of the carbons, the orientation of the groups or the configuration of the groups is same. So that means the whole of the molecule will stay like this. Only at first carbon, OH will be at the top of the ring. So this is how you'll convert. Now quickly what we've done, this is very important, convert Fisher to Horvath, or which is they can, if you're taking a multiple choice question as in NEET. So what you have to remember is, that is we'll make a cyclic structure which is having O at the right hand corner, top right hand corner. All the groups which are on the right will be at the bottom, group which is at the left, OH which is at the left, will be at the top, and if it is the alpha anomer, OH will be at the bottom in the first carbon, and the CH2OH which is and the OH will be trans to each other, and when CH2OH is at the top, it indicates that it is having D configuration. So quite simple, you don't have to do the mechanism. So why is this Haworth projection so useful? It is very useful because they allow us to see easily whether the OH groups are on the ring are cis or trans to each other, and if the OH group, that is the CH2OH group, primary hydroxyl group, and the OH at the first chiral carbon are trans to each other, we come to the conclusion that it is the alpha anomer, and if they are cis to each other, the orientation is cis like in this structure, then we say this is the beta anomer. And since the CH2OH is on the top, we say it is the having the configuration capital D, and of course you know that this plus indicates that this molecule is dextrorotatory, right? So this is how you will convert a Fisher projection into a Haworth projection. Here again I have magnified the structure and again shown you the structure for cyclic structure for glucose, that is the Haworth projection, and this is known as alpha D glucopyranose. Why alpha D glucopyranose? Because it is a cyclic structure of glucose, pyrane because it has the basic ring structure of pyrane, OS because it's a carbohydrate, D because the configuration at the highest carbon is the OH is on the right hand side, and alpha because this primary hydroxyl group and OH are on the opposite side of the plane of the ring. But now the question arises that does glucose occur as a pyranose rings in nature? Ask yourself a question. So what it is, when we look into the Haworth structure, what we find that Haworth's pyranose rings represent a glucose molecule as a planar structure that you've already seen. But we know that this glucopyranose structure is a 6-membered ring. Since it is a 6-membered ring, that means its structure should be similar to that of hydrocarbon cyclohexane. And we know that cyclohexane prefers to stay in a puckered structure or in a zigzag structure so that the steric strain is minimum there. Dipole-dipole interactions are minimum there. So what happens now is that the 6-membered rings of glucose like to occur in a zigzag conformation, and we know that is if we are comparing the chair conformation with the boat conformation of cyclohexane, the chair conformation is more stable. So that means now glucose molecules occur in nature in chair conformation. So now I want to discuss with you as to what is the chair conformation and how can we convert a Haworth projection to chair conformation in the whole mechanism as to how will we change it, and then of course the shortcut, some smart steps as to how we can convert it before, just not by looking into the mechanism, but I have to explain as to why we are doing it in long ways, so that because you know that when we are talking of Haworth projection, there the question does not arise of the equatorial bonds and the hydrogen bonds, but when we will talk of chair form, that means we'll have to take into consideration the equatorial positions and the axial position, and then we'll have to see as to where will we put the bulky groups which will give less steric strain or less dipole-dipole interactions. So what are we going to do? That let us see, we will first draw the chair form of cyclohexane and place the oxygen at the back right hand corner of the ring, and the primary alcoholic group in the equatorial position attached to C5 carbon. Why will we do this? Why will we put the primary alcoholic group at C5 position at the top? Because this is the largest substituent which is present in the glucose molecule. So see, what we've done here is, here you can see the structure of beta-D-glucopyranose, but just imagine these groups are not present there. So what have we done? We've made the chair form. With the top, this thing we've pulled down, and this is the rest, chair rest, and this is the chair head, and we put the oxygen here. Now this group will be the bulky group, CH2OH. Therefore, this is attached to the 5th carbon, and this is put at the equatorial position, because if it is put at the equatorial position, the steric hindrance will be less. So you have to keep in mind that when you are converting Haworth to a chair form, or when we are just drawing chair form, the larger substituents are to be placed at equatorial positions. Why so? Because at this position there will be less steric strain from the neighboring substituents. So the steric strain will be less because they will be further away from each other. Now, because we have to keep these groups at equatorial position, what we find that the group at C4 carbon will also be at equatorial position. And next thing what you find, as you've seen in the structure, that the OH at the 3rd carbon and OH at the 4th carbon are again at trans to each other. So that means we will put them also at the equatorial position. So that means we put all the hydroxyl groups in equatorial position in beta cyclohexane, beta glucose. So that means we have to now consider what will be the stability of the 6-membered ring. The 6-membered ring will be more stable if all the OH substituents are placed at the equatorial position, because then the steric strain will be less. And this is what happens in beta D glucose, that all the bulky substituents are placed at the equatorial positions, and hydrogens which are small in size, they are placed at the axial positions. They are placed at the axial positions because then they occupy less space, and therefore they will experience less steric strain. Right. So that means that beta D glucose is the most abundant of all aldohexases. Why so? Because it is existing in nature in chair conformation, in which all the bulky groups are present at the equatorial position and all the small groups are at axial position. So the steric strain is less. And we know that no other aldohexose will exist in such a strain-free conformation. So that is the reason why D-glucose is the most abundant monosaccharide in nature. So a question can be asked here, and this would be my last question which I am dealing here, that is as to why D-glucose is the most abundant monosaccharide. So your answer is going to be that it is D-glucose which occurs in that conformation, chair conformation, in which all the bulky groups are at equatorial position, so the steric strain is less. So this molecule occurs in a strain-free conformation. Now in my next lecture, I shall be discussing again this structure in brief and comparing it to that of the alpha D glucose. And then we will compare the structures of cyclic structures, that is the Fischer structure, Haworth structure, and the chair conformation of glucose. And for this you can also refer to these references to the bibliography which I am sharing with you. That is, you can go through the books by Carey Francis, McMurray Jones, Wade, Claydon, and Solomons. The concepts which I have discussed with you are very well explained in Solomons. With that, we end the lecture for today. Thank you.